And now, without further ado, we would like to start our second presentation. But who will be the presenter? Our second presenter is coming from Montana, US, and he's John, and he's functional programmer, author, speaker, entrepreneur, and longtime software architect and engineer. He is currently CEO at Ziverge, a company using functional programming to change the world. So please welcome on stage John A. DeGoose with building bulletproof concurrent applications on the JVM. Huge applause to John.
Thank you for that. Good morning, everyone. Welcome to my talk. Thank you for coming. And before I get started today, I would love to thank the organizers of this event for the invitation to speak here. It's been a while, actually, since I've been to Budapest, since pre-pandemic. But I love the city. I have an I Love Budapest t-shirt, which I did not bring. I am not used to this warm weather. I was expecting something chilly, and so I dressed all up in warm clothing, and I'm regretting it now. Anyway, I'm John DeGoose, and I am here to speak to you about building bulletproof cloud applications on the JVM. I'm going to talk to you about 7 challenges of building rock-solid cloud-native applications. And then I'm going to talk about some of the technologies that you might consider adopting in order to make it easier to build these types of next-generation applications. And then I'll finally wrap up with a summary at the end. So 7 challenges of cloud applications. These are 7 that I picked somewhat arbitrarily from a hat. Obviously, building a cloud app is not a simple thing, and there's really hundreds and hundreds of challenges across all the different areas of everything from engineering to testing and monitoring, observability and DevOps and whatnot. But I come from a background as a back-end software engineer, so this talk is going to be geared towards back-end software engineers and the concerns that they have when they're trying to build rock-solid cloud applications. Number 1. Latency. So latency is actually extraordinarily difficult to do right in cloud applications, and that's because you've got your cloud app that's talking to this Amazon web service over here, and it's talking to this other microservice, which is talking to another microservice, which is talking to a database, which is talking to your auth layer, and building low latency applications in the cloud is actually extremely challenging. And not only is it challenging, right, but it's also pretty important. I was surprised to learn that Amazon did a study about 10 years ago showing that for every 100 milliseconds of latency that they add to a page, it decreases revenue by 1%. That's amazing. It's not as amazing, though, as if you're building a trading platform and every millisecond, over 5 milliseconds, that you add latency ends up costing you $4 million. $4 million per millisecond of latency. Isn't that amazing? And Google has done some studies. They know if you add half a second to the page load time of google.com, it decreases search traffic by 20%. 20% for a company that derives almost all their revenue from advertising on search. That's how powerful latency it is. Now, many of us don't work on the types of applications where we're going to be hemorrhaging money at quite that rate if we're a little slower, but we can all benefit from low latency applications. High throughput applications. So we don't just want to minimize the amount of time it takes to service a request, but we also want to maximize the number of concurrent connections we can do at the same time while maintaining quality control standards. And whether you're doing low volume, hundreds of connections per second, or if you're in a high volume industry, you're probably looking at tens of thousands, hundreds of thousands of concurrent connections per second to your back-end system for a very popular mobile app in streaming or gambling, gaming, something like that. Scaling to hit those sorts of throughput numbers is not an easy task. Robustness. So we all are humans. We make mistakes, and when we make mistakes, our web servers go down, and they generate junk like this in log files or in public APIs, and this ends up costing the business money. It costs the business money every time our application goes down. Now, we want to build robustness into our applications. We want to build apps that don't go down. They don't go down because of bugs we made anyway. Maybe they go down for other reasons because Amazon went down. But ideally, we want to build apps that don't go down because of mistakes that we made as programmers. We also need to be able to handle the fact that Other systems we're interacting with are very flaky. And sometimes it's not just the systems, but it's also our pathway to get to them. We've got to interact with this API over there, and that API, and that database, which is locked because someone's doing something they shouldn't in that database. We've got to build resiliency into our applications, and resiliency is the ability for us, our applications, to handle transient failures in external systems. Correctness. We don't often think about software this way, but we want to build applications that are correct. They don't go into the unhappy path. The unhappy path, in some cases, can literally cost you tens of millions, hundreds of millions of dollars. Fortunately, we don't work in industries like that. But if you're working in blockchain or in fintech or some space like that, a single programming error, such as the overflow example showed here, could end up costing you tens of millions of dollars. Even if we're not in those domains, though, we still want applications that are to work correctly according to specification, because if we don't, we're going to end up losing some money out of that. Unhappy, disgruntled customers who go elsewhere. We also want applications to be very efficient. We don't want them to consume unnecessary resources. Now, a friend of mine was working for a video streaming company whose monthly Amazon bill for a single analytics service was $1 million a month. And he was senior architecture. He worked on the problem for a couple of months, came up with a way to get that down to $100,000 a month. Massive savings. 1 million to 100,000. And it matters, right? In many different companies around there, it doesn't matter what domain, we're spending a lot of money on Amazon. As you can see, that's Amazon's revenue chart, okay, in case you can't tell. And that's going straight up. We're all spending a lot more money than we want to on Amazon Web Services. And you build efficient applications, you can end up cutting down your monthly infrastructure costs, which is something that's going to make the CFO very happy. And finally, productivity. These cloud applications that we're building, given the fact that they have to be low latency and high throughput, and they have to be correct, and they have to be efficient, and they have to be resilient, they have to be robust, it's not so simple to build them. And we move very slowly in this environment of building cloud-native applications. And our product managers are always saying, move faster, right? Increase velocity. You heard that from Randy's talk earlier in the same room, if you were here. We need to find ways to be productive, despite the fact that building cloud-native applications is really quite challenging. So what can we do? Well, there's a bunch of different ways we could tackle these problems. We could look at programming languages. We could look at people and processes involved, bring better process and training, education, all of those techniques. We could look at different frameworks that we might, or libraries in some programming languages that help us deal with some of these challenges. And then finally, we could take a look at tools. So software tools, cloud tools, all of that stuff. And all of these different areas, I think there's something to be said for all of them, right? You can leverage any one of these different buckets to make it easier to build, maintain, and deploy bulletproof cloud applications. But I'm going to drill into two specific areas that I happen to know pretty well, and I'm a big believer in. And one of them is JVM technology, and I'm going to make an argument here today that you might want to consider adopting the JVM for your next big tech project, or at least maybe not rejecting the JVM for your next big tech project, and I'll explain why in a second. And then I'm going to talk a bit more about an open source framework that I work on myself, that my company works on, called Zio, that is designed to offer a first-class experience for building these next-generation cloud-native applications. It's all open source. We'll talk about that later. So Java, I talk about the JVM, and people's eyes roll. Right? Java's dead, right? JVM is dead. Docker killed it. Containerization killed it. In the old days, people used Java because of jars, wars. They could ship these things out, and ops knew how to deploy them, knew how to run them. They could run them in a standardized way. And Docker came along and changed the game there. And what has Java left in its wake? Well, applets, right? This was the day when Sun Microsystems thought it was a great idea to embed an operating system in a plugin to a browser. And that didn't work out so well. And we laugh about that now, or at least should laugh about it. But then we compile C to WebAssembly and run that in JavaScript in the browser. So you can't tell if an idea is going to be winning or not based on how silly it is, because sometimes silly ideas just work. Slow startup time. The legacy of slow startup time. It takes 6 to 7 seconds to start up a JVM application. Wow, no wonder people are using Go. And then garbage collection pauses, the other legacy that Java has left us with. That's actually what a good GC pause cycle looks like, where your latency only spikes to 160 milliseconds regularly, quite regularly, actually. That's what it looks like when it's good. When it spikes to like minutes, you're in trouble. And then don't forget URL hash code and other numerous blunders in the history of the Java programming languages. Did you know that adding a URL to a map inside the Java programming language might take 10 minutes? And that's because when you add something to a hash map, it computes the hash code. And it computes the hash code, it tries to standardize the URL by using a DNS resolver. And that process is going to actually use a socket blocking network connection to try to resolve the DNS. And if the timeouts have been set up appropriately, you could be waiting 10 minutes before you succeed in adding that URL to a hash map. So why am I trying to talk you into using the JVM after the legacy that Java has left us with? Well, I'm going to point to that guy. And actually, I'm going to say this is the most important thing you can take out of this talk today, is none of the technology, but go read his blog post, Samo Burya's blog post on live versus dead players. He talks about, this is a component of his great founder theory, he talks about a distinction between a live and a dead player, and the distinction is this, at least the most important distinction is this: a live player acts in new ways, has the capability to act in ways they've never acted before. A dead player just follows a script. They do the same old thing. Dead players are very easy to predict. And in a competitive market, you want to compete against the dead players. They're going to do the same old thing they've always done. Live players, though, you don't want to compete against a live player. Live player is Jeff Bezos, who started selling books. And now almost all applications, web and mobile in the world, are running on his platform. Live players are the dangerous ones, the ones you need to watch out for, because they can do anything. You cannot predict what they're going to do. They will respond to feedback, and they will act in ways that they've never acted before. That's what makes them so insanely dangerous in competitive markets. And looking at the history of Java, I see a lot of Java being a dead player. Okay, the great founder theory is designed to apply to individuals and to small individual collections of tightly coordinated individuals, but also applies to languages, programming languages, and companies, governments, countries, even libraries and frameworks, really. There's a way to think about it from that perspective. And I see a whole lot of Java being a dead player in its history. A whole lot of not doing much. And then something interesting starts happening around 2016. And Java, under Oracle, which is ostensibly a dead player, I might get in trouble for saying that. Oracle has lots of great technology, but they act in very predictable ways that they've always acted, right? They're never going to be doing something radical like Bezos or Jobs did. Something interesting happened around 2016. They start cranking out release after release. They're going to Java 8, 9, 10, 11. You're just on and on and on. Relentless pace of releases, getting stuff out the door. And they started changing the language. They started changing the language in massive ways. They started adding lambdas. They started adding vars and pattern matching and type inference. They started actually modifying the JVM. And that's not an easy thing to do. The JVM is basically like its own virtual machine. And so they started adding, I'm in deep trouble. I'm going to talk very fast towards the end of this presentation, but I really like this part. So the Java, they started adding things like Loom and ZGC and so forth, Graal, to change the very nature of the Java virtual machine. These are not superficial changes in a language, although they've made plenty of those. These are deep, deep changes. And I'm going to drill into a couple of them that I think might be relevant for building cloud-native applications. One is ZGC, which is a new garbage collector. I have another relatively new one called Shenandoah as well. This one's even newer. And what it does is it basically trades off throughput for latency, like the Go garbage collector. A Go garbage collector, super low latency, but not so great at throughput. And Java has historically been very high latency, but very high throughput as well. And what ZGC and to a lesser extent Shenandoah do is they manage to get latency down to an unheard of level. Basically, you can almost do real-time applications if you're using this GC. And that's extraordinarily impressive for new garbage collectors to come out and alter the JVM landscape in such a major way. It's truly amazing. To address JVM startup times, Oracle has come out with this project called Graal. And Graal literally takes application startup times from seconds down to a couple of milliseconds. And it's a total game changer for using JVM platform for things like AWS Lambda. Any low latency, if you need fast startup times, Graal makes the JVM competitive here. And then probably the biggest change of all that I'm going to talk about today is something you're lucky to see once in the history of a programming language. A change this big, you're lucky to see. So Java early on made the decision to expose a multi-threading model based on operating system threads. And there's lots of great reasons for doing that. One not so great reason is that operating system level threads don't scale very well. So they make it harder to build high throughput applications. And what Go has done is introduce Go routines, which are basically green threads. And Elixir and Erlang green threads. Green threads are much more lightweight than operating system level threads, and they make it very, very easy to build high throughput applications without having to work for it. What Oracle has done with Project Loom, which is now shipping, is they've managed to seamlessly go back and retrofit virtual threads, so green threads, into the JVM, so that now all of the code out there in the wild that looks like it's using actual operating system level threads can be powered by green threads. That's enormous. To change from OS threads to green threads and do it in a backward compatible way that simultaneously upgrades all of the millions of Java projects out there to green threading, that's amazing. That almost never happens. That would be like C++ deciding, oh, we're going to add garbage collection. Forget malloc and new and all that stuff. We're going to change and give everyone garbage collection. That doesn't happen, right? It did happen in the JVM. And the speed with which it happened is amazing. I mean, it took a couple of years, but the fact that it just took a couple of years is pretty amazing. Another great argument for using the JVM is that you get the diversity of multiple languages. It's like the .NET argument. Basically, .NET brings a whole family of languages. And it's the same thing with JVM. You actually have the ability to write your applications in Java or Kotlin or Scala or Clojure or one of any number of other different JVM languages or languages that happen to run on the JVM like Python and JavaScript. The ecosystem in Java is enormous. So that's the total number of repos on GitHub that are based on the JVM, 25 million. Of course, we know most of them are like, hi mom, I'm on GitHub now. Not very production worthy, but still, if you look at all the Java projects out there, Java is number 3. The only 2 languages that have more production-grade projects out there are Python and JavaScript. And then the ecosystem is phenomenal. Basically, if you're launching a new cloud service or a cloud platform or whatever, the first thing you do is you write the Java SDK. Well, actually, maybe it's the second thing. The first thing is the JavaScript SDK, and the second thing is the Java SDK. But basically, if you want a library out there to do something, if you want to interact with some cloud service, if you want to interact with some command line thing like Git, I guarantee you there's a Java library that can do that for you. All right, so the JVM actually tackles some of these challenges of building cloud-native applications. Some of the innovation lets us tackle the traditionally high latency of these applications, increase the throughput, increase efficiency, and also boost productivity of developers through a greater ecosystem and more diversity of languages. But that leaves a lot of things that are not touched at all by the choice of the JVM platform. And also, you could argue there's some other stuff to be done regarding some of these points. Like, JVM is not the only story to making highly efficient or low latency applications. We need more. And what is that? Well, we need, of course, a framework. We need a framework to build our application. Frameworks greatly accelerate the development of our applications. They give us guardrails. They give us the best practice. They factor out all the duplication from the web backends and other sorts of applications that we build, and they let us focus on delivering business value. They give us a whole bunch of tools just richly integrated out of the box for solving a particular problem. And yeah, we probably have too many frameworks on the JVM, but at least we're not JavaScript. We're not getting a new framework every other week like JavaScript is, so it could be worse. I'm going to talk for a few minutes about Zio. And Zio is a next-generation framework that's designed specifically for building cloud-native applications. And its claim to fame is that it's powered by statically typed functional programming. It's a functional programming-based framework, which is kind of cool. And I know what you're probably thinking when you hear functional programming, right? You've heard something in the back of your mind, like Haskell, right? Monads, category theory, this, that. Isn't that for all the nerds in their ivory tower who like building beautiful things that don't actually work in the real world? Well, the style, the flavor, if you will, of functional programming that Zio champions is very down-to-earth and ordinary. No terminology, no esoterica, no abstractions, no type classes, no category theory, nothing other than tools to help you solve specific business problems. This is a new take on FP, but make no mistake, it is functional programming. It's the good type of FP, like React, for example. React is probably the #1 framework in the world for building front-end web applications in JavaScript. And the idea behind React is actually very functional programming in nature. It's, let's imagine our entire view as a function from state to the HTML. Wow. That's one of the most mainstream examples of success in functional programming the world has ever seen. And it's not in your face, and you don't have to learn anything. It's just a great idea. And Zio is trying to give you that take on FP. I don't have time really to cover all this, but it's, as you would expect, high-performance, non-blocking, concurrent non-blocking queues, hub streams, maps, basically all that concurrent machinery out of the box, ring buffers, in case you like the high-performance, low-level data structures for building high-performance data engineering pipelines. It's completely testable. It has baked-in retries, repetition, and scheduling, very powerful automatic error management that results in you never losing errors anywhere over your entire application. Integrated metrics logging and tracing, dependency injection, very powerful HTTP, GraphQL, and microservice support, and it's built on JVM and Scala. And there's a few companies using it. Examples of some of the big companies using are Disney Streaming and Capital One and DHL and so forth, lots of these companies. Zio was released about a year and a half ago. And till that date, these are the companies, some of the companies, many more, who have started adopting Zio, and some of them for quite significant. For example, Capital One is using Zio to modernize all their infrastructure. They're one of the biggest banks in America. And Disney Streaming is using it to power a lot of their infrastructure for their new online streaming video platform. The core idea of Zio is very simple. It's basically thinking about our programs that we build as values. If you think about a workflow or a task, an interface in Java with a run method. There's this interface in Java called runnable. It just has one method called run. Zio takes that idea of, let's think about our program in terms of tasks, right? Or maybe some of you have heard of the command pattern, right? That's the command pattern there. Think of our whole program as being maybe built up from things that look like that. Only Zio takes the idea a bit further. It says, instead of just a task that you run, let's have that task return a success value. And let's use generics so that we can talk about the success value for all of our little tasks or workflows. And let's not just use a success value there. Let's introduce another type parameter to talk about error values. Because if we have a type parameter to talk about error values, we can talk about this task here failing in this way, or this other task not being able to fail at all. It allows us to think about error management at compile time and use the compiler's help to catch bugs and fix them before they happen. And Zio takes that one step further and says, well, maybe a task actually needs some input to run. maybe it needs some context. And that's the core idea behind Zio, is that every task needs some context to run. And when you do run it, it's going to end up failing with some value that's an error value, statically typed, or a success value that's also statically typed. You can think of the Zio data type as encapsulating the idea behind a workflow. You've got some context, which could be database connections or API tokens or config that your task needs in order to run. And then the Zio task itself has a bunch of steps inside it, like acquire resources, run a bunch of things in parallel, do this, schedule that. That's the Zio task that describes the orchestration of whatever is required to execute it. And then it either ends up erroring or it ends up succeeding with some data. And you can view every layer of your application, whether it's a very tiny, like inside an individual function, or whether it's the entire app, you can view them all as Zio tasks. So it's a very modular, almost like Lego-like building block from which you can snap your entire application together. And how you end up building programs with Zio is you have methods on the Zio data type that allow you to transform one workflow into another. A very common one is timeout. So you call timeout on one of these workflows, and you get back another workflow that acts as a sort of supervisor that runs the first one inside it, and will retry it or time it out after a certain amount of time has elapsed. That's a sort of a transformer. It can transform one workflow. Timeout is a transformer, just an ordinary method. You call it on a workflow, and you get back a new workflow. And then the other type of method that the Zio effect has on it is operators to combine effects. And there's multiple ways you might want to combine two workflows. Sometimes you want to combine two workflows together, and you want them to run sequentially. Other times you want to combine them together and have them run in parallel. And Zio gives you a whole host of, actually dozens, hundreds of different ways that you can either transform these Zio workflows or combine these Zio workflows. And this ends up opening the door to a new way of programming that lets you solve problems that were previously intractable, untractable, whatever the word is. All right, so some of these tools, I'm going to give you a real fast tour. I'm going to have to show you code, unfortunately, but a fast tour of some of the ways in which the Zio framework helps you solve the problems, the challenges of building cloud-native applications. Number one, latency. So Zio makes it extraordinarily easy to parallelize computation. So it's so easy and so cheap because, for another reason I'll talk about later, you can insert parallelism concurrency everywhere in your application. That enables you to drastically reduce application latency, doing more things in parallel. For example, in the top line of code, there's a loop over all the shopping cart items, and they're added individually to an order. In Zio, you actually could change that top line into the bottom line, change for each into for each par, and now the adding of those items to the shopping cart is going to happen in parallel. And Zio has many operators like that make it super easy to do things in parallel. Now, Zio is also capable of increasing application throughput, and it does it actually pre-Loom. So Zio is written in Scala, runs on the JVM, is optimized for Loom, but if you're not running on that version of the JVM that just came out, if you're on an older version of the JVM, like many companies are, you can still get the benefits of these virtual threads. And Zio does this through something called fibers. And fibers are super cheap. They're basically green threads, but implemented in a library. And you can have potentially 1 million fibers executing concurrently on a single machine, whereas the upper limit for real operating system-level threads on a single machine is roughly around 10,000. And this lets you, in this example, I create 100,000 fibers. Try that with threads. It's not going to end so well. Robustness. One of the things that Zio does to give you the ability to make very robust applications is it tracks errors. It uses the compiler to track errors at compile time. What that means is you can, for example, I can look at the type of that subscribe user function, and I can see its error type is nothing, and nothing basically means it can't happen. It's a special type in Scala, it means it can't happen. You look at a type like that, and you see subscribe user can't fail. And then in your implementation, of subscribe user, if you call a method that can fail, then the compiler helpfully reminds you. It says, hey, you told me that this method can't fail, but actually you can fail here. You need to handle this error and do something with it. You need to catch that error and do something with it. That gives you the ability to write applications whose error behavior is fully specified at compile time. You can look, you can hover over different parts of in your IDE, and you can know, can this fail, and if so, how it can fail. In addition, it gives you the ability to do sort of lossless translation of error between different parts of your system. We all build web servers, or at least most of us have built web servers in our life or web APIs, and one of the things that you have to do is reliably translate errors inside your application into response codes for the end world. And through this benefit of statically typed errors, Zio can use the compiler to help you make that translation. Because if your method says you're going to fail with a response code, and you actually fail with an I/O exception, then your compiler is going to say, hey, you need to find a way to turn this I/O exception into a response code. And that's up to you to decide how to do that. In addition, Zio has an extraordinarily powerful facility for building resilience into your applications. So you call some flaky API, you can call .retry on it, and you specify a policy, retry policy, a schedule actually. And these schedules are compositional, actually compose with intersection, union, and other types of things, geometric intersection based on intervals. This gives you the ability to build very fancy schedules, such as this schedule here that recurs 20 times with exponential fall off for as long as the error type is recoverable, and then add some jitter there to make sure that we don't synchronize our retries on a recovering web service. That's trivial in Zio. This and a billion other different ways to handle flakiness are trivial. And then for correctness, Zio, this is one example of the way that Zio uses the compiler to help you write correct code. Here we've got a Zio effect that in its type, you know that it opens resources. I won't explain all the details, but you can look at its type and you can know this opens resources. And then you enclose this in a scoped operator, and that allows you to use all the resources inside that code block. And then when that code block ends, the resources will be safely released. And the type changes. You see the type scoped changed to any. Basically, the scoped went away. The resources have been all closed. So you can know, looking at different parts of your program, whether any parts are using resources, and you can safely combine them. It's one of the tools that Zio gives you to build safe applications. In addition, Zio gives you strong testability. And by strong, I mean you can even adjust the clock and simulate what will happen in the passage of time. And all of the machinery built into Zio just sort of automatically does the right thing. So if you don't want to have sleep in your time, if you want to like fake sleep, but you want to create realistic situations for testing against, you can use the strong support that Zio has for being fully testable out of the box. Zio is extraordinarily efficient. It's actually very lazy. And it will try to always do the minimum amount of computation necessary. In the case of this little stream-based code that builds a stream of bytes, basically, from a SQL query, you can actually return this stream in your web front end. And if your JavaScript client only consumes half of this, then only half will be pulled from the database. So all that's extraordinarily lazy. Zio is maximally lazy. And that means you end up saving a lot of infrastructure costs. Not only that, but for example, one of the operations Zio gives you is the ability to race two different workflows. The loser of the race will be canceled. If you do something in parallel, if you do a whole bunch of things in parallel, and one of those things fails, all the other ones, which are currently running in parallel, will be canceled automatically. If you time something out, you can time out any workflow in Zio. Once that limit is reached, 10 seconds say, everything will be instantaneously just shut off, terminated, canceled, all resources will be cleaned up, allowing you to build applications that resource box requests. I mean, you never want to spend more than 10 seconds on a given request. You don't want to run away request that spends 2 minutes generating massive PDFs that are going to cost you a bunch of money. And the productivity, Zio is built at a high level in this fluent API style where you can just sort of dot chain methods together to do stuff. And that allows you to, in a small number of lines of code, solve very complex problems. Here, this is word count. in a few lines of code that will operate lazily in memory, in a tiny amount of memory, efficiently. If anything goes wrong, everything gets cleaned up and shut down. And also, you could change that to be concurrent if you really wanted and process word count across a whole bunch of files. And if you want to see me blunder my way through coding, live coding, they said you should never do it, and in fact, you should never live code, but I live coded a massively concurrent web crawler here in that presentation, which might be fun to watch sometime. All right, so in conclusion, we want to build bulletproof cloud applications, and it's rather hard because we've got to manage low latency and high throughput and efficiency and correctness and robustness and resilience and also be productive doing all of that. And I would encourage you to take a closer look at the JVM, especially if you rightly dismissed the JVM at some point in your history because of the problems associated with it. Take another look, because things are changing, and the JVM has never been a more active place, I think, of innovation in its entire history than right now, at this moment in time. And who knows? I have no idea what Oracle is going to do. They could do anything. 2 years from now, the JVM could be even better than it is today. I certainly wouldn't be too surprised if that were to happen. And then there's lots of great web frameworks out there. We have Spring, Quarkus, Micronaut, and whatnot. My own personal favorite, of course, is the one I work on, Zio, which is a very new web framework that's designed for cloud-native web applications, powered by functional programming. So please give that a try. All right, that's all I have for you. Thank you very much for attending my talk, and I don't know if we have time for questions. I guess I'll find out. Yes? No?
You can have your applause. Yeah. Thank you. This is for you, John. Thanks a lot from the name of Craft for being here with us today. We will have a little bit shorter time for a Q&A because I think everybody's hungry now. And we have only 5 minutes, so let's check Slido. What do we have? Phones in hand, guys, and let's see on top. As a Java developer, do I need to learn Scala to use Zio?
Right now, yes. That is true. You will have to learn Scala. But the nice thing about Scala is that, well, IntelliJ IDEA can translate your Java code into Scala. But it's not too unfamiliar. Like, it's the JVM, right? It's in the family. So you already know about methods, you already know about classes, you know about class loaders, you know about garbage collectors. You can use all the same libraries, you can call into your same code. The syntax is a little bit different, but I've seen Java developers pick up the Scala syntax in a week or two.
Cool. Seems that Zio is a combination of reactive patterns with explicit error handling like the ones seen in Golang. Is that assumption correct?
Yes. So I think that Zio learns from sort of the reactive manifesto and just this next generation philosophy of building fast, low latency, high throughput applications. And you can see a lot of that design philosophy reflected in Zio, but it adds, it's like, let's do more, right? Let's try to use our compiler to help us build correct applications, correct by construction applications. And that's coming from the FP influences in Zio.
How Zio tackles blocking calls. This was hard to crack for Project Loom. This took them the last couple years.
Yeah, great question. So, and even Loom has not entirely addressed blocking calls, right? Because there's still a few areas, like, for example, file I/O is still entirely blocking. They secretly use blocking thread pool to manage that, but it's still blocking. And it's not just that, unfortunately, but anytime you use synchronized, the synchronized keyword in Java, that's going to block. That's going to block. All the lock stuff, however, is totally async. So Zio manages it through a dedicated blocking thread pool, basically, which is best practice. So everything in Zio is 100% async. It's non-blocking. But if you use something outside of Zio, like file I/O, that's a great example, that is blocking, Zio will monitor your application, detect the fact that you're blocking in these threads, grab that piece of work, that executing workflow, and shift it over into dedicated blocking thread pool. That keeps the throughput of your main sort of CPU async thread pool very high. Keeps the throughput of that thread pool very high, but lets you do the stuff that you have to do because you're calling some blocking API over in a dedicated space to do that.
Okay, on top, what makes Zio more cooler than similar frameworks like Akka?
Well, I would say that a lot of, from my experience, a lot of people are ripping Akka out and replacing it by Z. I've talked to so many companies, and one company, for example, saw infrastructure costs go down to 30% of what they were on Akka. Not only that, but Akka, it's not designed for testability. It's actually quite hard to test a system built on Akka. And Zio is designed from the ground up with developer experience in mind. I'm passionate about nothing more than developer experience. I want things to feel good, to look good. I want things to be easily testable. And a lot of the other Zio contributors who work with me on this project, we're all passionate about that. So testability is a high concern. Looking at your code and knowing what it does, just by reading it, is very important. You can't know that about an Akka system, and it's very hard to test them. That said, it's great technology. Akka is proven, so nothing wrong in choosing Akka.
Let's see one provocating. Is the JVM actually innovating, or is it just haphazardly trying to catch up?
Is there a difference? Isn't that how we all innovate, right? Haphazardly trying to catch up? I think it's interesting that Loom, for example, did not modify the JVM bytecode, and in fact, these recent projects are not modifying the bytecode, and that's because the process involved in modifying the bytecode is monstrous and has to have so many people involved in improving that. So basically, right now, to innovate in the JVM, they're going around it and adding native methods in the Java that, for all intent and purposes, are sort of kind of like modifying the JVM. And yeah, they're trying to catch up, right? They're trying to catch up with Go and all these other programming. That's not a bad thing. Programming languages like Go are inspiring the JVM to catch up, and that's good. And I think that you're going to come out of that with something that's competitive in terms of sort of technology with Go, but with the gigantic ecosystem and installed user base that the JVM has built up over the past 20 years.
Okay, guys, we are out of time, so I would like to ask you to hunt him down at the lunch lounge. So if you want to ask a question of John, you still have time for that. He will be here on the conference today, I guess.
Yes, for a few hours I'll be here.